Good morning, everyone. Today is, what is it? It's April 25th already. Almost through the month of April here. And this is the John Chappell Natural Philosophy Society Science Chat. So let's see who we got here today. So we've got Dennis, we've got Bob, we've got Roger, we've got Bill, and we've got Ian. All right, so we have our full boatload of people here in the live room. So how you guys doing? Did you guys have any specific topics you might want to be interested in talking about today? What's been the burning question in your mind, or anything going on the email discussions? Well, don't all talk at once.
Okay, I noticed something in the emails which I hadn't been contributing to, going back some time, Franklin, about this old Galileo problem of dropping a very heavy object and a light object and finding how long it takes to reach the Earth. Well, obviously the Aristotelian view is that maybe a cannonball 10 times the mass of a smaller cannonball will only take a tenth of the time, and that's obviously not correct. And the Galilean principle, maybe dropping heights from the Leaning Tower of Pisa, is that they drop at the same time. But anyway, this email and paper brought to my attention the fact that actually they don't quite drop at the same time. There's a very, very small difference, because the larger object will attract the Earth a very, very small amount. So actually the distance that it actually has to travel is less. And the gravitational force is actually greater, because the relative gravitational force is not just G, say, capital M over R squared, the acceleration towards the Earth, but the relative acceleration is actually G over R squared into capital M plus small m, where small m is the mass of the object. So a large object will actually fall faster than a small object, but it's so imperceptible that it's the ratio of the mass of that object to the mass of the Earth. But it's
that again, because see, this is the thing I don't understand. So I've been kind of watching that same thread too, and I admit not really paying attention to what they're doing, because theoretically, the force is obviously different, but I don't know how they're calculating that it should drop faster. Are they actually calculating how it drops faster?
Well, I think yes. That's by the by. The speed is greater, because the speed is sort of proportional to the acceleration times time, and the acceleration is greater for the large object. I think there was one small error in the paper I noted. It actually makes the matter even worse, because I think he took the distance to be the same. Like he used the formula S is equal to say ut plus a half at squared or something, and he took the S to be the same in both cases. Well, the acceleration is actually greater in the case of the large object, which makes it fall very slightly faster, and it also
it shouldn't be. I mean, by what? Because the inertial resistance increases in proportional to the force. So it should be, and that's what the mainstream has always said, is that the acceleration should always be exactly the same. So how did they come up with even a small higher acceleration?
You see, I think that there are two effects actually, which I've looked at. One is the actual acceleration increases, and they've left out the very small increase due to the object attracting the Earth. You see, if you drop an object from a tower onto the Earth, it isn't true that the Earth is stationary, unless you're a sort of a geocentric person and the object falls down. But they actually approach each other. Now, obviously, the Earth being so much greater in mass will hardly move, but it actually will move, maybe a minuscule amount. And the larger the object, the larger. So, for example, if you had an object the mass of the Earth being dropped upon the Earth, they would meet at the halfway point. They would both, move that way. So you have to calculate the distance. That's one one parameter. Now, so the other parameter is actually the acceleration. So what people do, I don't even know if the mainstream might agree with me if I argued, but at first glance they'd probably say you're speaking rubbish, because what we're taught really, and what we plug into the equations when we're studying applied mathematics, is we say, well, say you have an object at small m and the Earth is large m. Well, then small m times g, acceleration due to gravity, is equal to g small m large m over r squared, in the ordinary denotation. The m's cancel out, so you get g is equal to large G times large m over r squared. However, that has neglected the acceleration of the Earth toward the object. So the actual full acceleration, the relative acceleration, is actually, in absolute space, if you like, is actually small m times g is equal to g times large m plus small m over r squared. Because there's an acceleration of the small object toward the Earth of g times large m over r squared. Yes? But there's also an acceleration of the Earth towards the small object, which is g times small m over r squared. And the net acceleration, therefore, is the sum of those. They're actually...
Okay, so I think I understand that the difference that they're talking about is that if you take into account the tiny acceleration of the Earth, that you're saying that the Earth is going to accelerate less towards your, whatever, the apple, than the bowling ball. What you're saying, the bowling ball will cause the Earth to accelerate faster than, say, an apple?
Well, you keep on talking about faster, and we can talk about that, but I think that's probably obfuscating the situation a bit. Just think in terms of acceleration and distance. So, if you do the two experiments at different times, if you drop the large object and then you come back a minute later and drop the small object. Now, if you compare those two separate experiments, you find with the large object, the acceleration is very slightly greater because of this additional small m over r squared times g. But also the distance is less because, I said to you that they meet halfway if you have equal masses. Well, it obviously meets, approximately at the Earth's surface, but the Earth has moved maybe picometers or something. I don't know, you could calculate it. I haven't done the sums. So there are two effects there. The gravitational effect is greater, and also the distance is less. Now, I did a thought experiment, which wasn't in this paper, but I said, well, suppose you do the two experiments at the same time. Suppose you drop the heavy cannonball and the small mass from the tower at the same time. Well, then they will both be attracting the Earth. So the distance will be the same in both cases because you've dropped the two of them at the same time. So the distance will be the same. But the acceleration on the large object will be greater. So only one of those effects will take place instead of the two effects. So
in that case, then they would still hit the Earth at the same time, then, right?
No, they wouldn't, because the time. Well, basically, the distance, assuming they're dropped from rest, is equal to a half times the acceleration times time squared. So the time is the square root of 2 times the distance over the acceleration. So since the acceleration is less for the smaller body, the time is greater. But even though the distance is the same.
I'm still not convinced that the acceleration would be different. I mean, I might be convinced that the Earth might move a little bit less for the big object versus the small object.
So I think see, there are two effects that I think, unless I'm talking nonsense, two effects that I have sort of adumbrated, and you accept one of them. You accept that the distance, if I do the two experiments separately, you agree that the distance for the large object will be less because it will attract the Earth. I think you accept that. But if I do the experiments together, I claim that it's still the large object will fall in a smaller time, and that's because of the acceleration effect. And you seem to be denying that, or you don't accept it. I could try to explain it again. I don't know if I did a very good job of it, but you understand what I mean about relative acceleration. You have to take the two terms into account. So strictly speaking, in the sort of solution of the Newtonian orbits of planets, we really should have g times large m plus small m over r squared, not just g times large m over r squared, as appears in most textbooks.
There's another fact.
Yeah, I guess I never quite thought. I mean, normally it's presented, big M, little m, and the forces are equal and opposite, so we don't analyze those two things differently. So, although
I think little m is so small, it's so minuscule in comparison with large m that you can neglect it. I mean, it's the order of m over small m over little over large m, and that's the reason they do it. It's not really. I thought it was in terms of frames of reference. I was looking at using the frame of reference of the Earth vis-a-vis the frame of reference of absolute space, but it didn't seem to matter because the total acceleration really is the sum of the two, because one is accelerated towards the other.
Okay, let's see here. We have Alistair. Alistair says he would like to weigh in on the subject. Ha ha ha. Okay, go ahead, Alistair. You there, Alistair? Your mic's open.
Can you hear me now?
Yeah, we can hear you. You're kind of quiet though. If you can get closer to your microphone.
I'll try. One thing to consider is the system is closed because the weight of the objects were already pressing down on the Earth when they were held at the top of the tower.
Yeah.
So we need to consider that they were at the same, that they were being initially held. So how does that make a difference?
Well, I'm just saying when you let go of both of them, you've released from the Earth the weight of those objects being held at the top of the tower.
So before they let it go, then they were initially pressing down on the Earth,
weren't they?
Yeah,
they were being held up by the tower, so they were pressing down on the tower.
And then when we let them both go, then suddenly the ball is the balls are free to move, and then the Earth is free to move.
And so if the supposed difference is the Earth moving up towards the heavier object, since they're both dropping at the same time, the Earth's movement up is equal for both of them. So aren't they both going to hit at the same time?
Yeah, Ian, I think that's what you were saying, right? If you did the thought experiment where you do both at the same time.
Only if you do it sequentially, do one after the other, then you isolate out the motion of the Earth from the one experiment to the second experiment.
Yes, that's what I've said. Yes.
Yeah. Agreed.
But Ian, you still think there's a difference, right?
You could think about it with if you had the whole human population, so they equal 1/12 trillionth of the mass of the Earth. So everybody jumps up at once. The Earth moves 1/12 trillionth of the distance that they jump in the opposite direction. The Earth is propelled by their jumping. So let's say they jump 1 meter. The Earth has moved 1/12 trillionth of a meter in the opposite direction, but then the two move back towards each other. Humanity falls back to the Earth, and the Earth falls back up towards humanity by that 1/12 trillionth of the meter. And that relates to what Ian is saying, is that a heavier object moves the Earth more. If one person jumps a meter, the Earth moves by 1/8 billionth less, because there's only one person, not 8 billion people. So then when
Bill's holding up his hand, Bill.
He's falling a slightly less distance than the 8 billion people would. By that one 8 billion.
This what we're talking about is
Bill's turn.
a smaller effect than the effect of the air on the falling of the object. And if you want to have them fall in a vacuum and you put them in a big vacuum tube, now you've got a third thing you've got to deal with. And but anyway, normally it's the air pressure that makes a difference. And you can see this in the extreme case. If I have a balloon and I have a ball of metal that weighs the same and I drop them, well, the balloon will be much slower getting down. And we'll see that. In fact, if a balloon has got hydrogen or helium in it, it'll go up instead of down, even though the force of gravity is still the same. And so we've got to take that into account. And we've never been able to fully test it, because if we put everything in a giant vacuum, then we've got to take into account the whole vacuum container, and that's just even more complicated. So,
Oh, you mean what? We have to take into account the gravitational force created by your vacuum container in that experiment?
Yeah.
We'll say when they did the experiment on the moon of dropping a feather and the hammer, I think it was, and finding that they fell at the same time. Well, obviously that was a very rough and imprecise experiment. It did show roughly the effect of air resistance on the Earth that you talk about, Bill. But I maintain from my preliminary analysis that if you did that experiment accurately on the moon, you would actually find that the hammer travels in slightly less time than the feather, but it'd be very, very slight amount.
Yeah, well, the moon doesn't have as much air as the Earth. It's much weaker.
Well, but I mean, there are sensational headlines coming out of this type of thing. They say Aristotle was right. Well, no, I'm not saying that. Aristotle was wrong, because he said these things should travel very much faster. I'm saying there is a minuscule, theoretically very small amount by which they would travel faster, travel in less time, and also if the experiments are done sequentially, travel a lesser distance for the heavier mass.
Well, I mean, I think it would be interesting if anyone tried to do a high precision test of whether two objects actually drop at the same time. I've done a little bit of research on this, and they don't actually test this by dropping two objects at the same time. They're actually measuring, it seemed like, something indirectly, which is I have to look up the experiments, but it's something like, because they're testing to see whether the inertial resistance is the same as the gravitational attraction, I guess, because it's all about the proportionality of the mass to the inertia, right? That's the way it's supposed to work. It's the reason why you have a bowling ball and it weighs 10 times as much as some other ball. The bowling ball has, it's registering like 100 pounds worth of force. And the other ball might be registering only 10 pounds of force. And the reason why they fall at the same time is because the bowling ball has 10 times as much resistance to acceleration, because the increase in the inertial mass. So if they can establish that the inertial mass is proportional to the gravitational mass, then they conclude that the two objects must fall and hit the ground at the same time. Although that is still like a theoretical consideration that they can experimentally measure out to arbitrary number of digits that the gravitational mass is the same as, well, proportional to the inertial mass. And then they just do their math. I think that's basically how they do that. But I don't know that anyone's done like a precision drop tower test or something where they really, dropped a light different object versus or even like measured different kinds of, like, that does wood fall less fast than, say, I don't know, lead, or it's got a styrofoam bead versus a gold sphere, things like that. I don't know that we've actually done experiments like that to the precision required to say that they really, fall and hit the ground at exactly the same time. I mean, it'd be interesting, or I don't know, maybe someone has done it, but one way to think about it, and this is kind of like how, so surprisingly, Einstein kind of thinks that gravitational acceleration is the same thing as actual real acceleration. So it's as if when you put the two balls in there, that it's actually the Earth's surface which is accelerating towards them. And then if you thought of it that way, then you would think that as soon as you let go of the balls and they just become in free space, there's nothing acting on them, they actually stay still. And it's the surface of the Earth which is actually accelerating up, and then it would obviously hit the two balls at exactly the same time. That being acceleration, gravitational acceleration being the same as actual, the ground moving up towards you, because that's the only other way that you can create gravitational force. Actually, that reminds me of the new series that I have been binge watching, which is The Expanse. And the way that they create gravity on their ships is that the ships are built like skyscrapers, so that the floors are parallel to the axis. And what they do is they just keep their rocket engine on the whole time. So the whole time they're traveling, they're accelerating, and that acceleration, though, so say they accelerate at 9.8 meters per second by keeping their rocket engines burning, right? And then that would produce a feeling, a sensation on the ship, just like here on Earth. We just feel the 9.8 meter acceleration. We just, stuck to the floor. So that is certainly an interesting way of creating gravity. I'd never actually seen that concept in a science fiction program before. Normally, we create artificial gravity by, spinning around, creating the centrifugal force type gravity, or they're just like in Star Trek, they're just something under the floor which creates gravity, right? But in this show, they do it since apparently they have, like, I don't know, unlimited amounts of fuel, that they can, whenever they're traveling someplace, they can just continue to accelerate at 9.8 meters per second and create artificial gravity that way, right? But like I said, for the purposes of our discussion, if you were in that ship being accelerated 9.8 meters per second, and you got the bowling ball and you've got, a pea, and you drop them, then you would expect exactly that behavior, that they would hit the ground at the same time. Because when you let go of the pea and the bowling ball, they just stop accelerating, and then the floor of the ship, which is accelerating, will hit those two things at the same time. So, but I just thought that was a interesting way of thinking about it. So, Bill, you have a comment?
Yes, there's a lot more to gravity than we have been mentioning. For instance, the gravitational constant is the poorest constant that we have in nature, because it's not constant. If you measure the force of gravity to 8 significant figures, which you can measure, you'll find it changes during the course of the day, because the Earth consists of different materials as you go down toward the center, and the Earth is rotating, and different parts of the liquid center is rotating at different speeds, and they have a different gravitational force. So the what you see when you look at the value that they give for gravity, they give you a 3-digit value, but we can measure it to 8. But if you measure it tomorrow, it'll be different. You measure it the next day, it'll be different. And it's it's slowly declining, but it's going up and down at the same time at a much higher rate than the decline. And that makes these
Now, are you talking
experiments.
about the gravitational constant or the actual force of gravity? I could believe that the
The
actual
force of gravity. The force of gravity is changing. If I am
yeah,
if I measure the force of gravity over the continent of the United States at a certain height, and I measure it over the ocean at the same height, I get a very different, a much stronger value for gravity over the ocean than I do over the continent.
although I'm thinking the gravitational constant itself should be the same, and you should measure that the same everywhere.
Well, I've measured it in the laboratory, and you can see it going up and down in the course of the day.
Yeah, the actual force of gravity upon any test object. I could easily believe
it goes
that
up and
would
down in the course
vary
of the day.
wildly. But we also measure the gravitational constant in like these Cavendish-like experiments where they have some evacuated box and they have a big mass and a little mass, and they vibrate them and they find out, what is the gravitational constant based on that. Although, and I think that's, the constant that you're measuring that, only is good to 3 significant digits, which is, like you said, is one of the least precision for any kind of constant, right? All the other constants are known to have, like 16 digits, and gravity is only known to have like 3 maybe or something, which is just ridiculous. And the other interesting thing is that different people, they can measure that constant of gravity within the error of their experiment out to say 8 digits. And but different people doing different experiments come up with different gravitational constants depending on how they do it. I mean, I've seen a chart of it, and it's like they have all these different values for the gravitational constant, and it's just by convention that we kind of, average those things out, and that's the reason why the gravitational constant is not known to a high precision, because all those high precision digits just drop off if you start looking at all the various experiments, which all seem valid, but all seem to be coming up with a different answer, right? It's not like they're inaccurate. It's like I'm doing an experiment and I get the number 6, and someone else does the same experiment and they get the number 4, and someone else does the experiment and they get 5, 10. It just and all these answers are incompatible with each other. So that is another interesting thing about, like you said, gravity is.
Well, the gravitational constant is just assuming that gravity is not a function of the electromagnetic situation. But Martin Spears has shown in his electrostatic theory of gravity that the reason that the little g, the value that acceleration at the surface of the Earth, it varies too much, even taking into account the rotation of the Earth and the local geology. And that's because of an electrostatic effect. Spears also gets the gravitational constant, large g, roughly in terms of some electrostatic constants, common electrostatic constants in the speed of light.
Yeah, I've always thought that a good experiment to do, like these experiments that are measuring the gravitational constant. Now, typically these are done in vacuum, but if you think that gravity is actually an electrostatic effect, then we know that the medium between the objects should have some effect on the strength of the attraction. So
yes.
I would think that
right.
Instead of, you should do the experiment, one in vacuum, and then find the heaviest medium you can possibly use, like maybe a xenon gas, just, fill it with pressurized xenon gas, and then do the experiment again. And I would predict that if gravity is an electrostatic effect, that we would see changes, predictable changes in the gravitational constant, depending on, what is the properties of that medium that you have in your test configuration. So it should be different from xenon, should be different from oxygen, should be different from, and you should be able to make some, equation relating what that would be. And then you could have to explain why you would get that difference. And perhaps the reason why you would get that difference is because like the permittivity and permeability through which the electrostatic force must travel through, it can be predicted to exactly equal those observed effects. And then maybe you could go back to the other experiments and point out that the reason why they got a different result was because the way their experiment was built. Maybe some experiments have better shielding, some experiments were done in air, some were done in vacuum, and see whether that's consistent with this idea that the gravitational force is actually an electrostatic effect. And we know that electrostatic effects, are very susceptible to, say, local shielding and stuff like that, right? So that would be my suggestion, right?
One comment I'd like to make is the Russians, Dmitriev and other people, have made crystalline balls of various materials, and then they have measured the force of gravity with those balls as a function of temperature. And they find that the temperature changes the force of gravity. And so when we are on the surface of the Earth somewhere and we're trying to measure the force of gravity, and the Earth is rotating and the liquid materials in it and some solid materials that are moving underneath the surface of the Earth, they are changing temperature as they rotate. And so we can see that, and we can see the effect. And so since there is a strong temperature dependence, it makes it very difficult. Even though we can measure things to 8 significant figures, it's not constant, but to about 3 significant figures. And so you got to take into account all these things. And if you say that the force of gravity is due to the average force between vibrating neutral electric multipoles, such as dipoles, quadrupoles, and octopoles, and you've got those in every atom between the electrons and the protons, you see that everything is changing, and it's hard to get anything very constant. And if you do experiments like the Russians have done, what they show is if I have a metal, say iron or something like that, and then I have it in crystalline form, and so it's forming a certain geometrical structure. As I increase the temperature, I break some of the bonds that are going on inside the atoms, and so it changes the vibration of the neutral electric multipoles, and that changes the value of gravity. And and you find this fully reproducible, and so that you can see the same effect over and over again. And many laboratories throughout the world have made that measurement, and it's well confirmed. So the force of gravity is not a constant type of force. It is due to vibrations of electric multipoles, and these vibrations are temperature dependent. And if I have a structure that supports, let's say, 20 types of vibrations in the crystalline structure, as I increase the temperature, some of the bindings inside no longer support that vibration, so that no longer contributes to gravity and causes gravity to drop in value. And then, but some of the others, as long as they remain bound and you give them a little bit more temperature, a little bit more energy, their vibrational energy goes up, and so it can cause gravity to increase as a function of temperature. So you have functions that you have processes that cause gravity to fall with increasing temperature, and you have processes that cause it to rise. And it doesn't agree with Einstein's general theory of relativity, E equal mc squared. The m is not a constant, which he assumes. And
looks like let's see, Ian's
Yeah, I'm sorry. I left the conference by accident because I was trying to find the reference to this paper. It's by a gentleman, I think it's Czech, Kanda, Kanda. Now, this paper, I've given the link in the chat there. He actually, his paper, I think, is basically about, a reanalysis of basic physics, contrary to special relativity and that sort of thing.
Is that
and this is the first part of
relativity page?
Pardon? At the beginning of the paper is what we were talking about at the beginning. And the only part that I disagree with actually is, although, mind you, Carl has raised another point we could look about the closed system, but I say there are two effects: the gravitational increase due to a larger mass, and also the distance, which is made shorter if the experiments are done sequentially. Now he just talks about the same distance. So I don't know, maybe he's envisaging the experiments not being sequential, but he only talks about the gravitational force being increased by the greater mass. It's a bit of a long paper. Maybe 80% of it is not on this subject, but anybody can study it at his leisure.
Well, you did send me this link, ending with P919. And that took me to the Physics Beyond Reality website. Is that the one you were talking about?
That's it. Now, I hope I don't lose the conference again by doing this, but
I can share this.
It said here, we're giving you this link. Let me just see, can I get the paper now again?
So, I mean,
it just redirected. It redirects you. Let me just see now. Oh, you're there.
The link that you sent me there, Physics Beyond Reality,
okay.
Has to do with.
Now, there's the lecturer there, and I think his paper can be downloaded there. Let me just. Your screen is a bit small, so I'll do it myself now. Go to that.
Which is all relativity stuff.
Yeah. Okay. Let me just see now. I've given you the right one. The gross of relativity. Have you tried downloading the Ghost of Relativity and Modality in Quantum Physics? I know that it doesn't sound a very promising title, but I think that's it.
Yeah, it says Newton versus Galileo.
Reclining experiment. It's how he starts the paper. That's right. Continuum versus physical continuum, mathematical continuum. Let me see now.
Does he mention whether, if you're going to have a paper that's doing this, a review of the actual experiments done?
I don't think he does. I think it's more.
Otherwise, it's all just a bunch of thought experiments, right?
Yeah.
What some people have said is not a real experiment, it's just a mathematical conjecture, is what, some people have said thought experiments are.
Yeah, but it's a little more. That's if I've given you the right reference. I mean, we're using well-established laws of physics, which have been verified by precise experiments, and we're just extrapolating them. It's like calculating the orbit of a satellite. You might say, well, before you've done that, have you actually put the satellite up and done the calculations? No, but we've based the orbit equations on well-known equations.
Now, it was my understanding that in the beginning of the space program, they did that, and all of their space probes, ended up crashing and such. Right, Bill, you have some experience in this, right? In the early days of.
Yes, I worked for NASA when I first got my PhD, and one of the problems they had was they were losing track of their satellites. They couldn't tell you where they were, and some of them were falling to the Earth, and others they just didn't know where they were. And the problem was they were not able to take into account the changes in the force of gravity as a satellite went around the Earth, and they were not able to handle on their computer what is called round-off error, which causes them to make their projections to get worse and worse over time. And so I helped them solve the round-off error problem, but they also, we put out rockets like Pioneer 10 and 11, for instance, in our solar system, and we found that our predictions on the force of gravity from the sun and the other planets was not accurate. There's errors there of some sort, and so what they did is they invented dark matter and dark energy to try and add on to what the normal theory of gravity was predicting, so that they could predict what is actually observed. And
well,
so
that
they
still
did that.
sounds like Newtonian mechanics still works, except that you have to calculate it to a higher degree of precision, rather than something more radical, which is that perhaps gravity is not a 1/r² kind of force, but you don't know anything about that. That's
they know. That's why they invented dark matter and dark energy. The current theories of gravity, due to Einstein's general theory of relativity,
well, I'm
and
not
Newton's
talking about
universal law of gravitation,
galactic.
they both fail. They both fail to predict what is observed.
Yeah, well, that's galactic. I'm talking about just like the practical problems of sending, say, the man to the moon, just between here and the moon. Whether you know of anything that would not be consistent with Newtonian mechanics, like you have to add some fudge factor to 1/r², so that when you launch your spaceship, you hit the moon. But I don't know that that there's anything like that.
Well, the when you take it off from the Earth's surface and go up into space, the temperature drops, and that causes the mass of everything that you're working with to change. And so, if you were calculating how much rocket propulsion I need to get to the certain place like the moon, you'll get it wrong if you don't take that into account. So,
well, do they? I mean, do they take that into account? Because I don't know all the deal. Because I saw this one reference basically saying that in order to send a rocket into proper orbit, if you go straight Newtonian, it ends up in the wrong place, and that they have to apply, rule of thumb things that they just learned from experience to put it in even approximately the right orbit. Because when they launch a satellite into orbit, they just kind of lob it up there in the general vicinity of where they want. Then they check to see what the orbit is. Then they have to apply thrusters to get it in the exact orbit that they want. Now, that seems a little bit strange, considering that, we can launch a ballistic missile from the United States, hit someplace in Russia, like 4,000 miles away, with an accuracy of about 50 feet, but we can't send a satellite into perfect orbit in one shot, right?
That's because the force of gravity is changing continuously as the satellite goes around in its orbit, and they don't know how to predict it. They do know they can measure it's changing, but they don't know how to predict it, and so that it's always you have to continually measure things continually. That's why they're using inertial propulsion now, is because that gives them the ability to continuously correct the orbit and get it so that it's where they want it. Because if they don't do that, then they eventually lose the satellite. They can't.
Well, I'm just kind of wondering whether all of the propaganda that we give about our nuclear arsenal being able to hit something that accurately is just a lie, right? Because I can't. It's just
they're using GPS. GPS will get you within 50 feet. The GPS that the tractors use is much more accurate, but it's not military based. And so,
And even military base, it's like, how can you launch a chemical rocket from, say, United States, hit someplace as far away as Russia, and not miss by like a mile, right? It just seems inconceivable. But I do know that, the United States government is very interested in things like gravity surveys. So apparently they take this into account, that when they launch their missiles, they have to take into account their gravity survey so that they know what it's going to do because of the varying gravity. And, I would think you would have to do that in order to have any hope of having any accuracy. Like that.
I think, Franklin, up to now, we've been talking about tweaks that are needed, either applying classical physics correctly, where we hadn't done so in the past, or because of other effects, atmospheric or temperature effect or so on. Now, with your permission, I'll give you another link that I was referred to recently. I've just put it in there, and it's the other thing. It's what we're more used to speaking about. It's saying, well, classical physics is not sufficient, and what they're claiming is that they've I don't know if you saw this. If you look at that link, they're claiming that they have witnessed a star making a precessed elliptical orbit about a black hole, and therefore proving Einstein is right again. Now, I wrote back to my correspondent, if you want to have a look at that link there, that they're obviously drawing an analogy between the planetary precessions of elliptical orbits and this supposed rotation of a star about a black hole. Now, I said, personally, I don't think that the less than 1% correction that's needed between the observed precession of the perihelion of say, the planet Mercury and that predicted by classical physics, less than 1% difference, it justifies introducing a whole new concept of curved space.
well,
Have you had a look at that link, by the way, Franklin? You see it there? Hello? You all gone? Is everybody there but Franklin?
yeah, I think we're all here.
Okay.
It's really tempting to stay silent and let you think you've been talking to yourself for 10 minutes, but no, I'm here too. I think it's just Franklin that's gone.
Okay. It's because I could, when he comes back, we could get him to share his screen. Are you there, Franklin?
Yeah, when I tried to share the screen, my browser just blew up. So
Oh, okay.
I don't know what happened there.
Okay.
So what happens when I disappear? You guys can still talk amongst yourself, right?
Yes. Yeah. Yes. But I don't think we could start doing things like sharing screens because you're the controller.
No, I think you can, right? I don't think that there's any restriction there to share the screen. Gee, now I'm kind of afraid to try it again, right?
Well, I could try it if you like, but then I'd have a problem probably.
Well, you can try it.
But how shall I share the screen?
Well, you've got your document up so you can see it on your screen.
Well, wait a minute. I haven't yet. I will in a second.
Yeah, get the document so you can see it on your screen.
Okay. Now it's up on my screen now.
And then towards the bottom of your screen, there should be a little share screen button. Do you see that?
I'll have to minimize this because it's filling my whole screen. No.
Yeah, you might have to. You have to see your StreamYard screen.
Well, no, even that is no use. I'll have to go back to StreamYard. Okay.
Yeah, you have to go to StreamYard. That's fine.
Yeah, right.
And do you see a share screen button at the bottom of your screen?
Yes.
So you click that, and then that will bring up another dialog, which will show you a picture of your screen. Now you also have to click in the middle of that to select, share your entire screen, and then click OK. And then I should see your screen show up as something that I can display. So you haven't done it so far.
Why not? I thought I had share your screen, your entire screen. Okay.
Yes. There you go. Share your entire screen and then click OK. Okay, so now
you can see it now.
Screen.
I'll go to the document now.
Yeah, now you go to the document, and so now we can see your document. Stars seen dancing around a supermassive black hole.
Yeah.
Once again, proving Einstein was right.
Well, that's what I said to my correspondent. I said, all these things are always proving Einstein is right. I said it's great publicity,
Except that thing about spooky accident distance. He was wrong about that, apparently.
Yeah, we came to that conclusion last time, didn't we? In quantum physics. Yeah. But I mean, there's a myth, which I was taught at college, unless, as I say, I didn't pick up the professor correctly. But the myth out there is that Newtonian physics predicts closed planetary ellipses and with zero precession, and that Einstein is needed to show this anomalous precession. But that's not the case. I mean, Newtonian physics predicts about 10 times this anomaly due to the influence of other planets, and it predicts about 100 times the anomaly due to viewing on an Earth whose equinoxes are precessing. So in other words, they say there's a difference of about 43 arc seconds per century. Well, we perceive about 6,000, about 5,600 of those arc seconds are due to the Earth's precession, and if you take that out, you get about 560 or 600 or something like that. 43 is less than 1% of that, and that could be accounted for by extra dust around the sun or other planets, or a greater revolution of the surface of the sun than its center. So it's a very, very small difference. So I'm not sure what this article doesn't refer to that at all. It just says, "Oh, hey, presto, we've seen this precession of an ellipse, and therefore it proves Einstein right." It's a very basic article, really. A star seen observing a supermassive black hole in the way that Einstein's general theory of relativity had predicted. Well, where's the anomalous precession that isn't predicted by Newtonian physics and is needed by relativity? He doesn't say.
I can tell you where it is.
Where is it?
If you look at certain types of graphs of the planets around our solar system, you'll see that the planets do not lie in a plane about the sun, that each of the planet's orbits are tilted with respect to the equatorial plane of the sun. And Einstein's theory of general relativity does not predict it, neither does Newton. And so none of those theories are able to describe the orbits of the planets correctly. And if you look at the orbits of the moons about the planets, they also have this irregularity. And but they don't make any they don't talk about it in textbooks or anything like that. I guess
we can't even predict the orbit of our own moon.
What I'm saying is the moon, the orbit is tilted with respect to the equatorial plane of the moon and the equatorial plane of the Earth, and if you look at if you were to do a graph of the moon going around the sun, it's got an elliptical path, but then it's got a rotation around the elliptical orbit that the moon has, and you don't have any theories that predict that. So you have to approximate it, and you have to do it by hand, and so that's not a good thing to do. These people that talk about the quantization of the orbits, well, neither Newton's universal law of gravitation nor Einstein's general relativity can predict the quantized orbits of the planets, and they can't get the tilt of the orbit with respect to the equatorial plane of the sun, and they can't get the tilt of the orbits of the planets about or the moons about the planets. So you've got all these data that we've measured very accurately, but nobody predicts it. And I've
Is
been
that
trying
something we need to predict?
Well, it shows your theory is false if you can't
No,
predict.
not necessarily. I mean,
Oh.
orbits, things can orbit in any way that they want. I mean, we can send satellites, polar to polar orbit or equatorial orbit. That's just a matter of how the object entered into the system.
Well,
I mean,
have you heard of the Big Bang and stuff like that? That sets the rules. And
but also the obliquity of the ecliptic of the planes, of the orbits. I mean, if they're slightly different, if they're not, if the slight variations, that is probably due to the initial conditions. I mean, how they originally, God knows, condensed or whatever, and took these orbits on. So it may not be an error. Like we may be expecting too much for any theory to predict exactly the orbits. I mean, as Franklin said, you could send any orbit up depending upon its initial thrusts and so on. So, I mean, if you put in those parameters, those initial conditions, the Newtonian system would work. But obviously, it cannot predict those initial conditions. That's true.
Well, that's why they've invented dark matter and dark energy, because they're trying to get a handle on that. And but there's so much structure of dark matter and dark energy that they need around every star that it turns out the universe is 96% dark matter and dark energy and 4% regular matter and regular energy. So you can see the part that we don't know about is 96% of the universe. And
that's crazy.
It is.
Well, I think we all agree that they're just introducing fudge factors. That's not proper science,
Well, the way we're doing science is we want to use the scientific method that is based on making hypotheses and testing them. We don't want to use the method that's based on logic. So we do not falsify any theories in modern science because the assumptions of the theories are false. We have abandoned that method, which was held for thousands of years. And so that's why none of the major theories in modern science are true. And the person who really showed that was the Frenchman,
Henri Poincaré, I think.
Henri Poincaré, yes. And the scientists hated him because he proved their theories were all false. And he developed the field of what's called meta theory with theorems showing that each of these theories are false. And they didn't like it because they wanted, for political reasons and other reasons, they wanted the theories that they had. They didn't want to have to replace them. And so that's what's been going on. But if you mention that at a scientific meeting and you work at a university or for some scientific organization, you get fired. I mentioned it one time and I was fired. I've never been able to get a job in the scientific community since that time. And over 500 people that have been in the former NPA have had that problem.
Yes, and furthermore, had that Silicon Republic article merely put that picture up and said, precession of a star's orbit about a black hole proves Newton was right, because Newton predicted precession. Well, if he'd brought that into his editor would have thrown him out. That's not interesting. Get out. That's not interesting. But if he says Einstein is proved right, well, yes, that's a great article. Put that down. It's good PR.
Yeah, since there's no more honesty among the scientists, there's no progress either, really.
Well, some people think that since about the mid 20th century, that we have made less progress. Like, for instance, in our standard model of elementary particles, we now have over 400 elementary particles, and less than 100 of them have ever been observed. But the theory requires it. And you see, we can't even predict the mass of an electron with the standard model of elementary particles. It's the worst prediction made by the standard model. And so, when you see all this, why don't we fix it? Why don't we correct it? And the answer is, if you try, you're out of the scientific community and you have to go do something else.
Well, I blame the mass media, basically, although I suppose I really ought to blame the scientists more for succumbing to it. But the mass media has driven this, and the scientists have shown their weakness by succumbing to it and feeding it and being led by it. So it's really, I'm not surprised if things got much worse from the middle of the last century. I'm not surprised, because the media would have been more powerful, and its ability to influence people and to influence governments and all that sort of thing, and get away from sort of what one might call pure thought.
Okay, so let's get back to what we were originally talking about, which is this whole gravity thing. I don't know that we've really concluded anything, because the effects we were talking about would be so small, it would be really difficult to measure. Like, you're never going to be able to measure the amount that the Earth moved towards a falling object that we drop on Earth that's of any size that we can actually experiment with. It may not even happen. I don't know. I could be a naysayer and say that no, that the Earth just doesn't move at all. It's not affected. I don't know, but
well, Dmitriev measured the temperature dependence of the mass for gravitational mass of various materials, and that's been confirmed. And you have a very high precision in those measurements, and no one's been able to explain, predict what he is seeing. They don't understand crystal structures well enough to do that, and the theories of quantum mechanics that we use are all known to be false. And so anyway, it's difficult to make progress under this system that we have. But we do have individual scientists who measure these things, and other people confirm what they have measured in other laboratories, but they don't want to make too big an issue of it so that they get in trouble. And yeah, it's a difficult situation. And see, we have what's called the postmodern philosophy of science now. So in the case of that, the people in chemistry find that when they change the temperature in a chemical factory where they're making things, they're changing the force of gravity that is affecting the products that they're making. And if they don't get it right, they don't get to make what they want to make in the chemical laboratory. And that's why many of these chemical substances are so expensive, because they have to do all kinds of corrections and things to make so they can produce the chemical compounds that they want. And if you don't do it right, and you don't get the force of gravity to be in the normal range, so it'll happen that way, you don't make that compound. And and that's why many compounds they make are so expensive, because it costs so much work to just figure out how to take into account the variable properties of gravity. And you're not allowed to publish any of that in a physics journal, just chemistry journals. And it's that way in each field. And so it makes it hard to share the information you have. And so we no longer have a university. We have a multiversity, where every field is a separate independent silo, and they do all their work independent of the others. And It's crazy. And you talk to people in the university, like the presidents and stuff like that, and they say, "Oh yeah, this is a problem, but we can't do anything about it."
Uh-huh. Let's see. I just came up with an idea. Why is it's not surprising why, say, a billiard ball and then say a ping pong ball should fall at the same rate, right? Now, another way that I thought of thinking about this is that, all matter, be it billiard balls or bowling balls, are all basically made out of exactly the same things, which is protons, electrons, and neutrons, right? So everything is made out of those fundamental building blocks. So far as gravity is concerned, the billiard ball and the bowling ball are made of exactly the same things, right? At a subatomic level, gravity is looking at the same thing. So, each one of those little pieces, like, this is a proton or neutron or whatever, you could represent it by, some amount of physical mass, right? Like this one little Lego brick, right? So if there's a force acting on the Lego brick, that's the force that acts on one Lego brick. And then if you have two Lego bricks, well, obviously the same force would act on the two Lego bricks. Now, it doesn't matter at all whether the Lego bricks are connected, right? Is there going to be any difference in the force or how this thing reacts, whether these things are connected or whether they're apart? And I would say, well, no, right? Why would they? And why should two Lego bricks attached together be any different than one Lego brick falling by itself, right? So, and then if you get things bigger, if I got a whole bunch of Lego bricks going together, then when I drop this, even though it's say much bigger than a little piece of it, still you have to think about the force on every little bit of this bigger thing being exactly the same thing as just the one. So in that way, intuitively, you would think that, everything should fall at the same rate, because if everything's pulling on the same building blocks, then it doesn't really matter that they're all conglomerated into some big gigantic thing. They should all fall at the same rate, right? And that if you put this thing on a scale, you'll see that that exerts far more force than what's a little piece of it would. But still, if the force of gravity accelerates any one little bit at a fixed rate, then it should accelerate a whole bunch of those things at the same rate. It's just like another way to think about it. If you have a ping pong ball and you drop one ping pong ball, it drops at a certain rate. You drop 10,000 ping pong balls, they'll still fall at the same rate, right? You wouldn't expect the 10,000 ping pong balls to drop faster, right? So that's one way of looking at it, in which case it's not that mysterious, I don't think, right? Not that mysterious.
Well, 10,000 balls is not very much in comparison with the mass of the Earth. But if you had, trillions and trillions of ping pong balls, they would, because they would attract the Earth, according to this way of looking at it.
No, they would. I mean, that's my point, is that the trillions of ping pong balls is doing exactly the same thing as the one ping pong ball. It doesn't matter that there's a trillion of them there. So I mean, when we're comparing the difference between, say, one place has got the trillion ping pong balls dropping and the other place has got just the one, and I'm saying that intuitively the trillion ping pong balls is just a trillion times the same as dropping the one, so they should all hit the floor at the same time. That's what I'm saying, right? Is that wrong? What do you think?
Well, I'm just speculating. I don't know the figures. It probably aren't.
Well, there's no figures. It's once again one of those
suppose the ping pong balls, trillions of them, equal the mass of the Earth. So you have a conglomeration of ping pong balls, but they're equal to the mass of the Earth. Well, do you not accept that they will attract the Earth just as much as the Earth will attract them, and that by symmetry they should meet halfway. And therefore
Well,
only go half the distance.
We're still talking about that little bit that the Earth might accelerate towards the trillion ping pong balls, I guess.
I suppose
He'll have to give that to you, right? That the trillion ping pong balls will cause movement of the Earth greater than the one.
Franklin, Ron Hatch has published a paper. He's a GPS expert that died last year. Paper, A New Theory of Gravity. And he explains why special and general relativity are wrong based on, see if I can get this in the picture. Special and general relativity are wrong based on GPS hard data. And, but he didn't have a PhD from a good university. So consequently, he or his colleagues in the GPS, which is now considered a wonder of the world, none of them got any kind of even honorable mention from the Nobel Prize people.
Yeah, Ronald Hatch. Now, what did Ron say exactly about what gravity was, or the equivalence inertia to gravitation? Lucia is saying that we're not talking enough about inertia here. The new theory of gravity, overcoming problems with general relativity. See, I hate that word, relativity.
Physics Essays, 2007.
You know, this discussion did bring up one interesting question, which is, Bill brought up the thing that, if you have a helium balloon, then that thing actually, rises, right? Now, if the force of gravity is equal upon all objects, including helium atoms versus oxygen atoms, then you'd think they'd all fall at the same rate. And so why does buoyancy occur, I guess, is kind of the thing that you can probably see buoyancy perhaps working when inside a large balloon, right? So, but at the individual molecule level, why does a helium atom go this way versus that way? If arguably the force is the same.
But I mean, it's the ratio of the volume of the molecule to the mass of the molecule. I know the individual atoms may be similar, but that's what gives buoyancy, because it's the weight of the displaced fluid, either air or water, which is giving you the upthrust, and that's balanced by the weight. So if you had a very small volume, well, then the weight of the displaced fluid will be very much less, and it actually would fall. But if you have a large volume with the same mass, I suppose that's what buoyancy is, isn't it?
Well, I've always thought, buoyancy is interesting to me because it's, if you think about it, the way we normally think about it is not really very precise. It's kind of like buoyancy works like two kids on a teeter-totter, and it's like the heavier kid is going to push the lighter kid up, right? And we kind of, if you ever like taking like a beach ball and you try to submerge it inside a pool, now theoretically what's happening is that the difference between the pressure on the underside from the mass of the water is somehow pushing that ball up from the underside. But it just really doesn't feel like that. It feels like that whole beach ball is just like it's got a rocket ship inside of it, and it's propelling itself. It seems to be propelling itself up. And if you were to like measure, say, the acceleration of it, you'd find out it accelerates up, right? It's not only being pushed up, but it's actually accelerating up as if it were some kind of anti-gravitational force, that the force of gravity when dealing with helium balloons is actually completely reversed. And that, while you might be able to explain, well, it might get pushed up or out of the way, it's harder to explain why it actually accelerates. It goes faster, right? If you have enough space for it to go, it goes faster. And the reason I mention that because, my theory of gravity is an electrostatic one, and there's a direct physical law that tells you that the direction of the force actually depends upon basically the polarizability of the medium, right? So it just happens that things which are denser happen to have the correct polarizability such that you get a force typically going down. But as soon as the medium has a polarizability that's less than the thing that you've got, like helium, then the force is predicted to be up, right? And so I'm saying that buoyancy is not due to this thing about like the heavier boy on the teeter-totter just pushing the other boy up. I mean, intuitively we think it's that, but it's actually that the materials itself, due to the electrostatic forces, is actually exerting literally. If you have a helium atoms inside an envelope of oxygen atoms, that literally that generates an upward force, that every one of the little molecules is yearning to go away from the gravitational field. And that's what we're actually feeling, not that there's this pushing force that's compelling the helium balloon to go up just because it's trying to kind of displace the lighter helium atoms. But it's a little bit hard to tell because you would have to put a force sensor on every little helium atom on your balloon, and you would have to see that it is in fact exerting a force going this way, and that's where the force is actually coming from. It's coming from inside the balloon, not around the balloon. So that would be the difference. So if you can kind of think of it that way, right? So have you ever thought about buoyancy that way, Ian, that really maybe it's not that simple intuitive thing, but perhaps that the force of gravity depends more upon the environment that you're sitting in rather than any actual absolute force pulling you down this way. Another way you could think of it is that if I had a pool of mercury, I could throw an automobile in there and the force of gravity would cause it to go up, right? Things like that, right? It's just like it, and these things would not work in the absence of gravity. So if you're in the space shuttle, an anti-gravitational environment, then you could stick something in the pool of mercury. It would be perfectly happy sitting in the middle of it, right? You have to have the force of gravity in order to exert that force, and that force depends upon the medium, right? Haven't completely worked this out because it would have to be something to the effect that density is directly proportional to that thing that the electrostatic force is dependent upon. And I'm not 100% sure that that's true. So what do you think about that speculation? That's a lot of speculation, but just trying to get you to think a little bit differently about buoyancy.
To give more thought. I mean, planes can fly, therefore, because of gravity. Ultimately, gravity is what keeps the atmosphere down. So, and that's assisting planes to fly. Yes, that's true. But we are so biologically geared to experiencing gravity within an atmospheric condition or within a fluidic condition that these things are sort of natural to us. And you're a bit surprised when you have to push down that ball and it rises because it's a bit irregular. But in our theories, we theorize about gravity in the absence of any of these buoyancy or atmospheric forces. That we postulate the vacuum conditions, and we say, well, what is gravity? Now, that might not be something that's valid in your theory, because you're saying it's intimately connected with the environment.
Yeah, medium. And see, that kind of implies that even in the vacuum, if you're sitting out there in the moon, and that's a pretty good vacuum, that there's still some medium must be present in order to give direction to the force of gravity. So,
well, that's only if your surmise is true.
Yeah.
If it holds, the case.
But it kind of gives you a different way of perhaps thinking about it.
Yes.
That there's something about density. I mean, definitely we know buoyancy has something to do with density, right? And that's a little piece that I haven't really nailed down, which is that density is directly proportional to the electromagnetic property, which causes this electrodiphoretic force, whatever, which is the force on neutral dipoles. So, because that's my theory, is that everybody's all atoms like that we normally have consist of neutral matter, which consists of charges, which is positive and negative. So everything in our body is actually some kind of dipole. And that all those dipoles are pointing towards the gravitational force. So that would be the other thing that you could predict, which I have not that much confirmation for, which that in general, when you're sitting on the Earth, that all of your dipoles are aligned towards the center of the Earth. That would be another requirement. And another requirement would be the actual force applied depends on your environment, such that if your environment is less dense than you, then the force is towards the gravity. However, if the environment is denser than you, then the force of gravity is that way. And it's exactly a force of gravity. The force you see up that we account for as gravity, as buoyancy, is actually the reverse force of gravity in that case. Of course, that's all speculation, and there's probably still a lot of holes in that, but that's what I throw out as a possibility. It's kind of a logical consequence of my own gravitational theories of it being an electrostatic thing. So,
well, getting back to the unequal masses just for a second. I mean, could you extrapolate that to the electrostatic case? We're normally doing experiments where we don't have very unequal electrostatic charges. Like we don't have a very huge charge with a minuscule charge. But I mean, if you had a large charge and then you have two charges, one which is 100 times the other, would that be accelerated towards the large charge more quickly, and therefore or would they fall at the same time? I'm trying to work out an analogy with the electrostatic Coulomb's law.
Well, you'd think, that's one of the main objections to an electrostatic gravity. And people think that, well, if you take something which is, say, the difference between a piece of plastic, which is a non-conductor, and highly polarizable, and a piece of steel, you'd think that if gravity was an electrostatic effect, that the differences in properties between those two things would cause them to drop at different rates. And the way I have applied that is that, well, maybe it does. And once again, this is the reason why we need to have actual high precision measurements of actual objects dropping, that we can't just measure the proportionality between inertial and gravitational forces, which is what we do, rather than actually drop two physical things. So if I drop a ball made out of styrofoam versus one made out of steel of the same mass, maybe you would get a difference, right? And that difference could only be explained by the electrostatic properties of the material, right? And the only way you could actually do that is by physically actually dropping two things, not just doing an individual experiment measuring the inertial mass of styrofoam versus the inertial mass of.
Well, of course, buoyancy would come in there if you did the experiment on the Earth, because the styrofoam would be gigantic in comparison with the steel of an equal mass.
You could work on that. I mean, you could make the styrofoam ball, compress it so that it's of the same density, whatever. But ultimately, it ends up being the same atoms, right? That was my point before with the Lego brick example, that ultimately everything is made out of protons, neutrons, and electrons, right? It's just different groupings of that same thing. Whether you're lead.
Hello, you've frozen again. Is it only Franklin?
Yeah, I think so.
Right.
Yeah, he's frozen.
Yeah, it's just when we get silence, you think everybody else has, but actually it turns out you're all there. You'll no doubt come back.
Apparently, the network for StreamYard is located in such a way that when Franklin freezes, or one of us freezes, it's because of our connection to that network, whereas everyone else who has an intact connection to the StreamYard network can still communicate with each other visually and with their voice. And end of story. Hi, Franklin. I think he's back. Is he back?
Yeah, I'm back. Whenever I get too close to the truth, right?
Yeah, I don't know if there's any reason why you're the one who's being cut off, despite what James said. Maybe it's linked or something.
Due to the fact that I, instead of renting the modem from from Comcast for $10 a month, I bought my own modem and my own router, and apparently it's kind of flaky. So, although I did hear that they're going to be forced to provide modems for everybody or something like that. Maybe I should just get theirs, because my connection is just kind of it doesn't stay up. It drops out occasionally. But yeah, that was kind of weird, right? So James, you are putting out some theory as to why the cutouts happen.
Well, yeah. I mean, let's look at what's going on here. I see 4 people on the screen, and all 4 are connected to StreamYard network. In other words, each of us has an individual internet connection to the central StreamYard controlling network. So if only one of us drops out, it obviously has to do with the connection of that one person. And in this case, it was you. Now down here, where I'm at, the company, or the internet company, if you will, is the telephone company, and they provide the router. You can't just go out and buy some other router. I suppose if you're technically competent in that, you might be able to do that. But so you might want to get the router that is provided by the communications company that you're using, Franklin, because there could be some subtle difference in protocols there that are causing you to flip out.
Yeah, I think so. That's the conspiracy, right? But I think maybe I can get the router from them for free now, rather than $10 a month, because I have to check that out. But clearly, what I have is not. It occasionally cuts out, not very frequently, but the first cutout was due to my browser crashing, so that wasn't due to my internet. But the second cutout was due to my internet actually cutting out. Occasionally, it just drops the Wi-Fi. I don't know why. So it's Comcast trying to get me. And I was talking about something important. What the heck was I talking about?
It's always the case.
Ian, what was I talking about?
Well, the electrostatic origin, or the supposed electrostatic origin of gravity, and when you analyze it at the atomic level, how that seems to be counterintuitive. I don't know if that's a summary of what you were talking about, an accurate summary, Franklin.
Oh, yes, very good, good. So glad someone was paying attention there, because that would be the one of the main objections to an electrostatic gravity, that the composition of the materials should greatly affect the gravitational acceleration, right? And
I would argue that against the atomic theory, as you say, everything is based on the same elementary particles. So why have you got styrofoam, and why have you got steel, and why have you got air, all made of the same elementary particles?
Chemical bonding.
Yes. So it's quite possible that you get quite different chemical, gravitational, completely different substances with different properties because of their chemical bonding and their whole constitution.
but if you are trying to support an electrostatic gravity, you would have to say none of that makes any sense. You know, whether it's a conductor or not a conductor, that it shouldn't make any difference. For example, if you're a conductor and gravity is this electrostatic force, for example, in my theory, it's just a constant positive force. So that would cause all the electrons that can migrate in your metal to migrate to the bottom. You know, like if the Earth is positive, all the negative charges would migrate to the bottom of your metal, and all your positive charges would migrate up to the top. And you would think that that would create a different force than, say, a block of styrofoam where the electrons are immobile, right? The electrons cannot move around like that, right? So you think
Franklin,
that
can I talk to this?
block
Can I
would fall
talk to this?
differently than the styrofoam block.
Can I talk to this?
Yeah, go ahead,
Can you
Dennis.
hear me?
We can hear you.
The thing about it is, it's really a capacitor theory of gravity, not an electrostatic. Capacitors have a property that if you have three spherical capacitors in a vacuum that are charged, say, positively, they will repel. But in matter, the electrons and the protons are pretty much equal in number and charge. So the charge sums to zero. But the proton has a much larger mass than the electron. And so if you model them as spherical capacitors, you soon find that the fact that these models then have to have very different radii, the spherical capacitors that are modeling the electrons and the protons, this causes a higher order anomalous effect, which turns out to be gravity, and you get the gravitational constant to three figures by fooling with this and using Coulomb's law. So it's this electrostatic gravity really means capacitor theory of gravity, where you're modeling electrons and protons as spherical capacitors, one electron with 1 unit minus charge, the proton with 1 unit positive charge. But the fact that they have different radii gives you a slightly unbalanced effect, even though the charges are assumed to roughly sum to zero. And that's why gravity is so weak in comparison with the electrostatic force of Coulomb.
Okay, I'm not quite sure I got that, although I do have a question from
Yes, go ahead.
YouTube here. So Musera asks, if I put a heavy horizontal magnetic field, do you lose weight in that case? So I would answer that by saying that I would not expect a magnetic field to change your weight, because that, generally speaking, doesn't change the dipole orientation, I don't think. But if you were to put yourself in a heavy horizontal electrostatic field, so if I have two Van de Graaff generators and one is strongly negatively charged and one is strongly positively charged, then I would think that if you can get your dipole stuff tilt away from the Earth, that you should probably be able to see a change in the force of gravity. So I should theoretically get lighter in that case. Now, definitely, if I had a very, very strong positive charge and I stuck it above my head, there should be some amount of electrostatic force that would actually make me weightless. And I've actually done that in small scale experiments. So I have like a Van de Graaff generator, which generates very high positive charge. And I routed that force onto like a small like Christmas ornament type ball. And I had a tiny bit of aluminum. I would I'd make a tiny aluminum cup and I'd suspend it on a nylon bristle. And I would do an experiment with, I would move that ball closer to the aluminum cup, and the aluminum cup would actually rise up. At some point, the force created by the Van de Graaff generator overcomes the force of gravity, and it actually physically rises up. So if you were to scale that up, then you could think of maybe like at the wrecking yard, they use a giant magnet to pick up cars. If they could create a sufficiently strong electromagnetic force, that would also pick up cars, right? The only problem being that the Earth itself generates a field, probably in the millions of volts. And if you were to try to generate a field of that strength in one little spot by basically ordinary charge displacement, then that would create a gigantic lightning bolt, would try and discharge that thing. So in practice, it's difficult to create such strong electrostatic fields. But that's something which is certainly possible. I mean, I have done experiments where I launched soap bubbles off of Van de Graaff generators. So Van de Graaff generates positively charged. So the prediction would be that the positively charged bubble would go up. And to the limited extent that I can experiment with this, they actually do that. I mean, it's kind of mysterious that these bubbles look like almost like they're filled with helium, right? They aggressively rise up into the atmosphere when they're positively charged, but when you turn off the Van de Graaff generator, they do actually fairly quickly drop to the ground. Right, this is their normal behavior. That soap bubble, no charge, drops to the ground. But the soap bubble charge, I mean, some of them still drop to the ground, but a lot of them just go up and away. So I can kind of use that as an example of and I'm thinking that from a practical standpoint, if you were to launch a spaceship, one thing that you could do to reduce your fuel requirement is just charge it up positively, and that will cause it to repel the Earth. Therefore, you need less fuel, right? So, I still got to write the letter to Elon Musk saying, if you just go and you charge your spaceship up as high as you can possibly go, maybe 300,000 volts before you launch, then your fuel requirement will be greatly reduced, right? And that's just based on. I mean, actually, you don't have to even believe in my gravity theory for that, because we can measure the electric field strength on the Earth, and it's not zero. It's quite strong, actually. Although the references I see are kind of conflicting on what's the polarity, right? I think the mainstream thinks that there is a polarity, but it's negative rather than positive, right? Now, it doesn't technically make any difference which way it is, but I still feel there's more evidence for it being a positive net charge on the Earth versus a negative net charge on the Earth. So, and that's just electrostatics. You don't even have to believe gravity is electrostatic. I mean, the electrostatic charge is there, right? You see thunderclouds, and that's also electrostatic behavior. And the funny thing that they can't complain about thunderclouds is that all of the positive charges migrate to the bottom of the cloud. All the negative charges all the positive charges migrate to the top, and all the negative charges migrate to the bottom. That's why we get this big charge differential. That's why we get lightning, right? But no one understands why that differentiation occurs, but it would make sense if the Earth was a big positively charged ball, that it would cause all the negative charges to head toward the bottom of the charge and all the positive to go to the top. That's just a natural natural thing you would expect if you're sitting in a field like that, right? So,
according to Tesla,
to use, right? I think if I charge myself up with enough positive charge, I would go floating off my chair. That would be my prediction ultimately.
Nikola Tesla found that there's a large electric capacitor electric field, the Earth with one charge and the ionosphere with the other, and between the two there's a very strong electrostatic field, but it doesn't cause any arcing ordinarily because air is such a good insulator. Air is such a good insulator. But Tesla found that the Earth's surface and on one hand and the Earth's ionosphere on the other hand are two poles of a spherical capacitor, one inside the other. It has a very strong electrical effect.
Yeah, there is the Earth is definitely an electrically active place. It's like the Earth gets struck by lightning, something like 3,000 times per second somewhere around the world, right? There's some definite electrical activity going on. So I would say that that electrical activity is actually what gravity is, right? They're one and the same. But Musser has another interesting question, which is, so what's the difference with electrostatic effects? Is it all the same? And that kind of comes up with the other objection to electrostatic gravity, which is that if I go and I stand inside of a steel ship, which is a Faraday cage, then I should be anti-gravitational, right? All the electrical field should be shielded from me inside of my steel ship, and I should become anti-gravitational, right? That would be the conclusion there. But obviously that's not true. It's like the force of gravity within the steel ship is, probably identical to me standing outside the steel ship. So what's the deal, right? So this has to do with what's the difference between electrostatic effects. So clearly this is true in small scale experiments. So if I go and I take my Van de Graaff generator and I have an electrostatic meter, and if I put my electrostatic meter inside the Faraday cage and I bring it up to the Faraday, the Van de Graaff generator, I'll see that the electrostatic field has in fact been blocked. And that does work. But I think that there's a difference between those kind of electrostatic effects, which are caused by actual charge displacements, right? The Van de Graaff generator is emitting that positive field because there's actually electrons missing from that Van de Graaff generator, and it's of a finite quantity, right? And because it's finite, then I believe that its effect is somewhat limited. It can be shielded by a simple Faraday cage, which, the number of atoms in the Faraday cage is relatively much compared to the number of electrons missing in the Van de Graaff generator. So it can shield. But if you had like a gigantic Van de Graaff generator, like the one they have in the Boston Museum of Science, I think that the shielding effect has a limit, that at some point the atoms in the shielding device will become saturated, and that they will themselves then transmit the electric field. And that would not be shieldable. So I'm just saying that certain electrostatic field effects can be shielded, but to a certain extent. And that the electrostatic field that the Earth would produce would be very much different than that produced by the Van de Graaff generator. In the Earth, what it is that you have an extremely diffuse charge on the Earth. I mean, really, it's like one electron missing out of every trillion atoms weak. But what happens is that there's a geometric effect that causes that charge to effectively sum up as if they were all in the center of the Earth, okay? So it's like you have this gigantic billion Coulomb charge sitting 3,000 miles away from you, but it's just the sum of all of the diffuse charges that are around you. But because it's diffuse, we don't get this big problem where you get some immediate discharge because of that displacement. It's like a phantom electrostatic field. It's like an electrostatic field, but without the discharge displacement. So I think that planetary gravity, if it's electrostatic, is of a very different nature than the local electrostatic effects that we can see with, say, Van de Graaff generators and Faraday cages down here. So, but eventually you would have to come to the point where the reason why you don't go float away in the battleship is because the metals, and in fact everything on the Earth, is completely saturated that the electrostatic field flows straight through it, and it doesn't see it. Because that's another mystery about gravity you have to explain, which is why can't it be shielded, right? So, and it can't. So, but that has to be explained. But I can kind of hand wave my way around it, but it's still hand waving.
It's partially shielded. That's why as you go around the surface of the Earth, you get different values of the acceleration due to gravity at the surface, because not only is the local geology different, some may have aluminum ore, which would be light, some may have taconite, which is iron ore, which is heavy, and then there's the rotation of the Earth. But even so, that doesn't, as Bill pointed out, even that isn't enough to get things more than 3 significant figures. And your idea, your thinking is wrong, and Franklin, I think, in that the Earth, if it were considered to be electrically neutral, which it approximately is, that wouldn't attract anything direct by Coulomb's law directly. But if it turns out the electrons on one hand and the protons on the other can be modeled as spherical capacitors, but with very different radii, since they have very different masses, then you get an effect from that would be a much more subtle effect. And so these problems that you mentioned wouldn't arise.
Well, perhaps, although it's actually relatively easy to think about how electrostatic gravity works, because the main thing that people don't realize is that neutral matter is attracted to any strong electrostatic source. So like if I turn on my Van de Graaff generator, if you actually measure the force on anything that's around the Van de Graaff generator, you find that it's actually being pulled towards it. Just like gravity, it's being pulled towards it. So it's
that's right.
Not a difficult thing to observe. I mean, that's something that is frequently ignored. That if you have the very strong electrostatic force, that anything that's neutrally charged, it doesn't actually matter what it's made out of. I have one of my videos on YouTube where I basically just charge up a comb or whatever. And then I can show that it attracts metal nickel, it attracts chopsticks, it attracts shit. It doesn't really matter what it is, but everything is attracted to it, right? So that it's not a very complicated or subtle thing for it to do that, but
no,
that's something that you can do.
Well, it's presumably inducing an opposite charge on those formerly neutral materials.
Well, no, you don't have to induce a charge. This is the trick, is that most people think that attraction has to be between opposites. So, when I suggest that the Earth is positively charged, and people think that, well, we must be negatively charged then. And no, that's not the case. We're not charged at all. That the theory is that your ions or your dipoles align so that the positive the positive charges are deflected upward and the negative charges are deflected downward. Now there's a little bit of difference, distance between these two. So now the negative charge is actually stronger than the positive repelling, right? So the negative charge wins. So it exerts downward force. And so the requirement is that the dipole do be aligned. Because if it's aligned this way, then there would be no net force, right? Although it would tend to want to twist this way, I guess. But,
well, another way of looking at it is that the lower surface would then have a negative charge, a net negative charge.
Yeah, and basically that's what we see in clouds. That basically the lower surface of gravity of cloud has a negative charge on it, right? That's what we generally observe. So we have some other interesting comments here that there have been experiments like that, and they have observed that at sufficiently high voltages, things do start to float. And I do have like this one interesting story about, a golfer. Golfers are always being struck by lightning, but some, like there was one famous incident with, I don't know, maybe Arnold Palmer. He says that he actually levitated off the ground at some point. I don't know if that's true or not, but that kind of behavior could happen. And some of the other interesting things is like they say that things like tornadoes are actually an electrical effect. That what you have going on there is that the tornado is not being created by this outward wind action, but actually the tornado acts like an electric motor. That it's actually forcefully causing the air to twist around what is actually an electrical discharge. It's actually like a lightning effect. And some people have reported, when they're in the middle of a tornado, seeing this blue electric arc going up through the middle of the tornado being actually an electrical effect. And, they've recorded these weird things where really heavy objects like cars just get, they'll just flip, or they'll just fly through the air. Things like cows suddenly become anti-gravitational. Now, maybe that's due to the force of the wind, or maybe it's because these objects actually lose their gravitational attraction, and that's why we can have flying cows and flying cars and cars that just do that. I mean, what kind of wind action caused two cars to go like that? I mean, that just seems inconceivable that things like that can happen. But if you think that the force of gravity has suddenly been released on these objects, then maybe that's it. But gravity could still be a separate force in electrostatics. It could still be. The electrostatic effect is going to happen no matter what, right? And so all we know is that the Earth is full of electricity. The electricity must have an effect. Whatever gravity is doing, right? You can't really rule it out. In fact, that's kind of one of my main arguments about this thing, is that even if gravity was something else, we can measure the electricity that's on the Earth, and we can measure the amount of force that would contribute to our bodies. And when I can make that calculation, turns out it nearly accounts for 100% of the force that we feel, right? So that would mean that if force was a different thing, that it would only account for 0.5% of the observed weight, because the other 98% is already accounted for by just the electric field that we're sitting in, right? So therefore, I conclude that gravity and the force caused by electrostatic field, that's exactly the same thing. But, I still have to explain these things. Why is I don't go floating off when I sit inside of a Faraday cage? Why is it that various different materials don't seem to fall at the same rate? It didn't seem to matter what their composition is, or whether it's a conductor or not a conductor. Those things don't seem to make a great deal of difference. So all I can do is, wave my hand and say that the force of gravity must actually act upon the individual dipole components in each atom. And whether you're made out of hydrogen, helium, carbon, oxygen, lead, those components are the same, and that is what it primarily acts on. And there could be some tiny differences due to the fact that, maybe some electrons do tend to migrate versus another material where it doesn't. Maybe that, but you'd have to have a super sensitive experiment to determine that. But looks like we've come to close to the end of our time here. So I'll just do a little summary here. So we started out with a little discussion started by Ian about, when you have two objects, heavy one, light one, this fall as right. And so observations done in emails showing that there's this difference in the actual acceleration of the Earth up towards the falling object. And therefore, the bigger one should probably hit sooner than the smaller one by some really, really small amount. And, well, maybe that's true, but no one's been able to actually do an experiment like that. I myself would like to see some precision experiments done in a vacuum drop chamber over some relatively large distances using really, really different weights, right? And then using different materials and to see whether in a live drop, whether those things actually fall at the same rate. I'm thinking that maybe they have done some experiments, but with like individual atoms and things like that, because they can do stuff like that. To see whether there is some difference or not. And let's see, what else did we get into? Yeah, we're talking about just gravity in general, and that it's really hard to measure. The force of gravity varies throughout the day. And the scientists can't even really agree on what the gravitational constant is. It's only known to say 3 digits. That's the only 3 digits they agree upon. Every experiment that they do comes up with a different number. And that perhaps that indicates that, and we explored the possibility that gravity is an electrostatic force, because you would kind of expect that if gravity has something to do with electrostatics, then your experimental setup will greatly affect what measurement you get out of that situation, because the environment is greatly involved in that whole calculation. So we explored that a little bit. So I gave you a little bit of little spiel on what I think gravity might be as an electrostatic force there. But I think that will do it for our time today. Thank you for Ian for bringing our question of the day. And we'll see you next week then. All right. See ya.